This video covers Module 8, Part 1. Module 8 is the final module in this course, which covers quadratic equations, inequalities, and their functions. So, in Part 1, what we're going to talk about is solving quadratic functions using the square root property and by completing the square. We've already solved quadratic functions before using factoring, and we're going to learn a couple more ways in this module. So, friendly reminder, a function f is a quadratic function. Previously, we called this like a trinomial function, but it has a special name. We call it a quadratic function if f of x equals ax squared plus bx plus c. This is like our standard form, and a cannot be 0. And the graph of any quadratic function is going to be a parabola with a vertical axis of symmetry, meaning it's going to look like this, or maybe it looks like this, but it has a symmetrical line right down the middle. So here's our most basic parabola. We've seen this before. This is the squaring function, and what it does is it pairs every x with its square. 1 squared is 1, 2 squared is 4, 0 squared is 0, negative 1 squared becomes a positive 1, and negative 2 squared becomes a positive 2. Its domain is all real numbers. This parabola, whose equation is y equals x squared, its range goes from 0 to 8, and to infinity. Wow, good morning. And its vertex is 0, 0. Its vertex is our origin. And what do I mean by vertex? Well, our vertex is where our graph looks like it's changing from having negative slope to positive slope. It's also what divides our parabola in half symmetrically. So here we'd have an axis of symmetry when x equals 0. Remember, if x equals a constant, its graph is a vertical line, and it has undefined slope. The last thing you need to know about the squaring function is it is continuous over its entire domain, and it is a function because it passes the vertical line test. So here's something we haven't talked about a ton, which is when I have a function and I set it equal to 0, when I let y equal 0, we're finding the x-intercepts. And we saw this with linear equations in Module 2, and we're going to do this as well in Module 8. But in Module 5, if I gave you a parabola like x squared minus x minus 6 equals 0, and I told you to solve this by factoring, you'd go ahead and factor, and you'd get two x values. X is 3, and x is negative 2. What you didn't realize at the time was that for our parabola, you were finding the x-intercepts. This parabola would have x-intercepts at negative 2 and a positive 3. So previously, we have solved quadratic functions, trinomials, by factoring, which I think is one of the best ways to solve them. And our goal is always to first try and find the factors of AC that add up to B. When we couldn't do that before, we called it prime. But in this chapter, we are learning ways to factor things that might appear prime to begin with, and how to find their x-intercepts. So first example, I've got x squared minus x minus 20 equals 0. This is a problem we solved a bunch of in Module 5. What are the factors of negative 20 that add up to negative 1? How about negative 5 and 4? And I can check my answer by FOILing this out. I set each of my terms equal to 0 and find that x is 5 and x is negative 4. These are my two x-intercepts. And you can see here, if I was to graph this parabola, I graph this in Desmos, I would find my x and y intercepts. Another way we can solve quadratic functions is using the square root property. And we touched on this briefly in Module 5, but now that we've completed Module 7, where we talked all about radicals, we can do that again. So if x and k are real numbers and x squared equals k, then we have x equals the square root of k or x equals negative square root of k. That should have been a k right there. We've seen this before. If I had x squared minus 1, this is a product of a sum and a difference if I factored it. And I would get that x plus 1 is 0, x minus 1 is 0. So x is negative 1 and x is 1. I also could have got my x squared by itself by adding 1 to the other side, taken the square root of both sides, and found that x is plus or minus the square root of 1. Well, that would be x is plus or minus 1, right? I'd get to the exact same answers. But sometimes numbers, like 5, for instance, don't have perfect square roots. So we can use this when we're working with them. So let me clear us a little bit more space. Now we've worked through a bonus example. All right, if I have x squared equals 5, I can take the square root of both sides, and I'd have x is plus or minus the square root of 5, and I can't simplify that any further. If I have x minus 5 squared is 36, I can take the square root of both sides. I get x minus 5 equals plus or minus 6, so I divide this into two equations. X minus 5 is positive 6, x minus 5 is negative 6. I add 5 to both sides because our goal is to get our x all by itself. And I get x is 11 and x is negative 1. Those are my two x-intercepts. Whereas here, I just left them as plus or minus square root of 2. I also could have written it out as the square root of 5 minus square root of 5. One last example, I've got 2x minus 3 squared is 18. I take the square root of both sides. I get 2x minus 3 is plus or minus the square root of 18, which is 3 root 2. I've got, I could break it up into 2 or I could leave it as is. I can add 3 to both sides. 2x equals 3 plus or minus 3 root 2. I divide both sides by 2. X equals 3 plus or minus 3 root 2 over 2. Okay. So a couple things to remember. One, when we are setting a trinomial, now we're going to call a quadratic function equal to 0, we're finding the x-intercepts. We solved these previously by factoring. We can also solve them using the square root property, which is going to be helpful for the next tool we're learning. But what do we do when they're prime? How do I solve something like this? Well, there's no factors of negative 7 that add up to 2. So previously what we've done is prime. But if I was to graph this in Desmos, which feel free to pause and graph this in Desmos, you're going to see you have two intercepts. It just so happens that those intercepts aren't nice integers. Maybe they're fractions, maybe they're imaginary. Well, you won't be able to see if they're imaginary, if they're intercepts. We'll come to that in a second. But maybe they're fractions, maybe they're irrational numbers. So we need another tool to solve this, and that's going to be completing the square. And the goal of completing the square is to be able to take your trinomial and add something to it so that it'll factor into a perfect square. So if I've got x squared plus bx is a binomial, and I add b over 2 squared, which is half of our coefficient of x, remember b is our second term, a is our first term, this is going to result in us being able to factor a perfect square. So let's do a couple of examples. If I've got x squared plus 8x, and I add 8, our b, divided by 2 squared, that's going to give me x squared plus 8x plus 16. Well, what are the factors of 16 that add up to 8? How about 4 and 4? That factors into a perfect square. The same thing works for problem 2 right here. If I've got x squared minus 14x, I'm going to add a negative 14 divided by 2 squared. Well, negative 14 divided by 2 is negative 7. Negative 7 squared is 49. What are the factors of 49 that add up to negative 14? How about negative 7 and negative 7, right? This is going to factor into a perfect square. What you're going to want to always do is take your middle term, divide it by 2, and square it. Take your middle term, divide it by 2, and square it. So how is this going to help me solve quadratic functions? So if I have a quadratic function, ax squared plus bx plus c equals 0, first things first, I would always try and factor it. I think factoring, it's a tool we already have. It's going to be the easiest way to solve these things, but let's say you can't. So for example, with x squared plus 8x plus 10 is 0, there are no factors of 10 that add up to 8. So there's no way I can factor this. We would previously have said this is prime, but now we're learning a new skill. I have to make sure my a is 1. So if my a doesn't equal 1, I need to divide each side of the equation by a. Second, we have to rewrite the equation so the constant term is alone on the other side of the equality symbol, meaning I need to move my c. I'm going to do that by subtracting 10 from both sides because 10 was our c. We've got a, b, c. That leaves me with x squared plus 8x equals a negative 10. Now we're going to add b over 2 squared to both sides. We have to add it to both sides because this is an equation. And what we do to one side, we have to do to the other. So I'm going to take 8 divided by 2 squared to both sides. We know that that is 16. I'm going to factor my left-hand side. And then I can use the square root property. That's why we had a nice little square root property friendly reminder that you have to rationalize all denominators. No radicals in our denominators if needed. So I'm going to take the square root of both sides. I get x plus 4 equals plus or minus the square root of 6. So x would be negative 4 plus the square root, plus or minus the square root of 6. That's our final answer. It's not the most satisfying answer, but it's the reason that we couldn't factor this trinomial originally, because my roots, my x-intercepts, were irrational numbers. Let's do a few more examples. So if I have x squared plus 5x minus 1 equals 0, I have to make sure my a term is 1, which it is. I move my constant to the other side. I'm going to have to add my middle term divided by 2 squared to both sides. Now we're going to have to work with a fraction, but that's okay. I'm going to have 1 plus 25 over 4. And then this left-hand side here, I could rewrite it like this. But one key point of completing the square is that it's always going to factor to x plus b over 2 squared. So I know that this is going to factor to x plus 5 over 2 squared. That's going to give me, well, 1, I can rewrite 1 as the fraction 4 over 4. So I'd have 29 fourths. We then take the square root of both sides. That leaves me x plus 5 halves equals plus or minus the square root of 29 over the square root of 4. Well, the square root of 4 is 2. I subtract 5 halves from both sides. I get x equals negative 5 plus or minus the square root of 29. Both of these are over 2, So I can rewrite this as -5 plus or minus the square root of 29 over 2. And if you're thinking, oh, the result of completing the square here looks kind of familiar, maybe like something I've seen before, maybe like something coming from the quadratic formula. Well, then you have a lot to look forward to in Module 8, Part 2. All right, this time a isn't 1. I've got 2x squared minus 4x plus 10 is 0. So I need to divide both sides of my equation by 2. That gives me x squared minus 2x plus 5 is 0. I'm going to move my constant to the other side. I'm going to add -2 divided by 2 squared. -2 divided by 2 is -1, squared is 1. This left-hand side is going to factor to x minus 1 squared. So I have x minus 1 squared is -4. I go ahead and I take the square root of both sides. So I get x minus 1 equals the square root of -4, which I can now do. That's going to be a complex number. That's 2i. So x equals 1, plus or minus 2i. This example has 2 imaginary complex number of roots, 2 imaginary x-intercepts, which means our graph, and we'll see more of this in a later chapter, later in this chapter, which means our graph has no x-intercepts, meaning my graph is kind of floating above the x-axis somewhere, and it never crosses. If you get 2 imaginary x-intercepts, that means there's no x-intercepts. Last example, I've got x squared minus 2x plus 7 is 0. Again, our a is 0, which is very nice. Not our a is 0, our a is 1, which is very nice. I subtract 7 from both sides. So I have x squared minus 2x is -7. I'm going to add a -2 divided by 2 squared to both sides. So I get x minus 1 squared is -7 plus 1. X minus 1 squared is -6. I take the square root of both sides. I get x minus 1 is plus or minus I root 6. X is going to be 1 plus or minus I root 6. So those are our steps for completing the square. Those of you going into pre-calculus and college algebra, first college algebra, then pre-calculus, are going to see a lot more of this. There are a lot of videos on my YouTube channel that are just me solving multiple, very many completing the square problems. I'll put a link in our Canvas course.